However, each of these that I was allowed into, they had separate folders and they had separate clips within them inside these three-ring binders. And I was told which numbers I was allowed to open up. And they were given to me on a card, and those are the ones that I was allowed to review during the times that I was allowed to review them. Most of the stuff, I mean, they had everything from military applications, the physics of the craft, and I couldn't have cared less. I was more interested in taking in the biology issues. Just doesn't interest me.
All right, what is up, you guys? Welcome back to another video. The last one was 6 hours long, and I called it Filling in the Gaps of Riemann's Habilitation Thesis, Differential Geometry stream, something like that. And that was filmed in like 2 or 3 days, 2 main sessions of typing out notes where I had spent several weekends working out the notes. And I'm going to be honest with you. So basically what it is I'll show the screen here. This is Riemann's habilitation thesis. And this is what kicked off Riemannian geometry. So these videos have all been called Differential Geometry Reading Stream. And it shows you what a novice amateur I am, or I was at the beginning of making these on the subject matter, because really you could break differential geometry, what's in the book I've been reading, Erwin Kreyszig here, if you don't already know. You could break that down into 2 main topics, or like subfields perhaps. You have smooth manifolds, and then you have Riemannian geometry. And then sort of to contrast these, there's topology, because the modern effort of differential geometry or Riemannian geometry or smooth manifolds research is, how do those things affect topology? How does curvature affect topology, and so on? But back in the day, the state of the art in Riemann's time was everything that Gauss had done up to that point. And so Riemann was in his like early 20s, probably like 24, 25, somewhere around there at the time. So he had already attained a PhD, and this is in Germany, keep in mind. And Gauss is his advisor, and the way it works is Riemann, the student, so-called, gives 3 topics to his committee. And the first 2 topics were related to something like, I don't know, like the Riemann integral or something like that Riemann had already worked out. And it's, you know, we already know about what that is today, even in like high school Calc 1, right? What a Riemann integral is, you know what I'm saying? Gets superseded by Lebesgue integrals, but that's a whole other thing, right? But it was sort of like the convention, or you would just expect that you'd give 3 topics to your committee, and they would pick one of the first 2, basically. So topic 3 for Riemann was on the hypotheses which lie at the basis of geometry. And Riemann didn't expect Gauss to pick that, because Gauss, Carl Friedrich Gauss, was, you know, obviously his name is on a ton of math stuff, but Gauss was like the plane curves expert at the time. You know, what was it called? The Disquistiones Superficies Curvas, something like that. That was like the big plane curves work by Gauss. So he was like, you know, anyways. But topic 3 was what Gauss ultimately picked for Riemann to do his habilitation thesis on. And stunningly, this was the result. And so, you know, I had read about everything that I basically just rambled to you from Wikipedia before I actually saw this document. So, you know, I'm already aware of books at that point like Riemannian Geometry by Peter Peterson. So that's like a modern math book, hundreds of pages. It's probably like 300-400 pages around there. And so I'm expecting at least like 100 pages for this Riemann habilitation thesis. But as you can see here, this whole entire document is 15 pages. Okay, I open it up and I'm like, oh, this is probably just like the abstract or like the first introduction section. No, okay, we've got a title page and then the whole enchilada, and then at the very end, we have another 2 pages which are a synopsis of like all the different headers that are in here. So it's like, yeah, this is a dozen pages, and it kicked off Riemannian geometry. And then we go down here to part 2, section 4. We're in part 3. Okay, this is part 2, section 4. And no context of any other math. Look at these just brick walls of text, basically. It's like, oh yeah, there's like ds equals. Okay, that's like nothing, bro. That's like no math, essentially. So then you come down here and you see this, and you're like, what is going on here? 1 over a denominator 1 plus 1/4 alpha times the sum of x squared, then times that's the fraction. Then we have times the square root of the sum of dx squared. You're like, what? And then, okay, so that's what this whole video is about, is then in the 6 hours, I came up with this. I call this the work of a reader to fill in the gaps of Riemann's über die Hypothesen welcher Geometrie zugrunde liegen, where I basically spell it out for you. This is really what the problem is. So I'm going to read this whole entire document basically because I figured, it's kind of like halfway between 6 hours unhinged, almost unedited. I edited stuff out where like I took breaks. And, honestly, the first time I wrote this document through, no references. This whole stereographic projection part, I had just kind of like in the middle of solving the problem. Because, spoiler alert, basically this form right here, this is vaguely related to stereographic projection. And yeah, that's kind of the point of this document. But also, okay, this is the last thing that I'm going to say before I actually read this. Okay, straight up, I'm not going to lie to you guys. When I first was deciding to undertake doing this, to fill in the gaps and answer like WTF is going on? Where did this come from? How does this mean that there's Riemannian geometry now? It's like, what? This document, I feel like I've answered that, at least for myself. But the first time I was like deciding to do this, I was messing around with Grok and Chat GPT and all that. And I was like, because everyone's hyping up AI, LLMs are like, oh, now you can ask it really hard math problems. I was like, oh yeah, bro. And so I would, obviously ask the statement of the problem, which is basically like, you have to figure out that this ultimately boils down to solving a partial differential equation, but it's like understanding where that PDE comes from, understanding how that relates to curvature and all the stuff that came before Riemann. And, this obviously ties to general relativity, because that's the other thing, is that section 3 of Riemann's habilitation thesis, basically it's like the kernel of the math that would eventually lead to general relativity, because in section 3, Riemann basically says that you could use this math to approach the like mathematical axiomatic underpinnings of what Newton used to come up with his mechanics, his system of gravity. And basically that's what Einstein did. So general relativity connection there. But it's like, okay, ask that to Chat GPT. Now, surely there were parts in here where I'm computing like a tensor contraction. I'm doing, Christoffel symbols, Kronecker deltas and stuff. And there's, partial derivatives intermixed. So like, the indices get crazy at different points in here. So like I fed the problem into those different AI whatevers, but certain parts in here, like I'm going to be honest, actually computing the Riemannian curvature tensor, That was kind of helpful from the AI. However, there's like throttles on how much output a non-premium user can get nowadays. So like I would be reading through this, like the answers they would output, these AI models, and it would just like cut off. Like there are parts in here where here's like this is just more foreshadowing. The Riemann curvature tensor has these like huge chunks here, like line 58, 59, 60. And it would kind of maybe show, for example, like, yeah, or like up here, it would show all of this 47 through 55, this kind of like brute force, tedious by hand calculation. But it would only do it for like line 45, like only just one part, which is just like line 59 right here down below. So it would neglect the other, similarly formed part of the problem. And so there were like parts that were missing like that, but then there were also parts, weirdly enough, like with Grok, I noticed, because I guess that one has had more recently like so-called math reasoning improvements. Especially when we're like actually computing, putting in the solution into the PDE, it would like break the rules of doing algebra, like what you learn in elementary or middle school, say for like doing algebra, and you don't get the answer that you want. You don't just write in, change the numbers while you're working with it. It's like, I don't know how else to describe it, but it's like literally a little kid would not do that kind of like. Anyways, so like weird stuff like that would happen. But then like at the end of the output that you would get, it would still be like the quote unquote correct answer, because it's like kind of inferred from what you put into the problem. It's able to Google search, scrape the web for what should the answer be that someone's written in a textbook related form, but it like screwed up the calculations in order to arrive upon that. So someone who's just like copying, pasting, and just, you know, Jesus takes the wheel with whatever comes out of the AI model, there are huge gaps still in the math reasoning, from my reckoning, with filling in the gaps of Riemann's habilitation thesis and understanding everything that comes with that. If it can be understood, everything that comes with this, that would be the unbounded and the infinite. So, this is not going to be another 6-hour long video. So, now we're going to get to the, I don't know. I'm just going to read this now. Okay, here we go. Introduction. The result worked out here is to derive a metric for a constant Gaussian curvature n-dimensional manifold with a locally Euclidean metric that is scaled by a conformal, that is, angle-preserving factor. This amounts to finding a solution of a form of the Liouville equation, a partial differential equation. The motivation is to demonstrate a solution of the Liouville equation for the Riemannian metric of a Riemannian manifold given constant Gaussian curvature capital K. The particular form of the Liouville equation here displays a solution that will resemble the stereographic projection formulae and connect to the result in Part 2, Section 4 of Riemann's 1854 habilitation Schrift dissertation, which hereafter will be referred to as Über die Hypothesen. See reference 1 at the bottom. The result in Part 2, Section 4 of Riemann's habilitation thesis is a classification result for Riemannian manifolds. Namely, for constant Gaussian curvature K, when K is greater than 0, it is called spherical curvature. K equals 0 corresponds to Euclidean or flat curvature, and K less than 0 is called hyperbolic curvature. Section 2, Background. The goal is to show that K equals capital R sub 1212 all over lowercase g implies that a fraction 1 over the denominator of 1 plus 1/4 alpha times the sum of x squared, then times the square root of the sum of dx squared. Roughly speaking, the left side of 1 above is a statement of Gaussian curvature in terms of a component of the Riemannian curvature tensor and a metric g. So that would be k equals r sub 1, 2, 1, 2 all over g. The right side of what is above is the result of Riemann's 1854 habilitation thesis. The only symbolic math notation expressed in the entirety of the dozen or so pages of Riemann's Über die Hypothesen, as it appears in the PDF, which I have over here, which is the English translation, is the right-hand side of what is above. It is implied that the expression on the right-hand side is an expression equal to ds, or the notion of infinitesimal arc length on the surface of the manifold. Essentially, the goal statement above, if you will, implies the gap that was left by Riemann for the readers of his habilitation thesis to fill in as an exercise. The more abstract goal is to better understand how to use metrics to determine lengths, angles, and areas, or in other words, how to use measure relations and magnitude relations as they perhaps were to Riemann on n manifolds of constant Gaussian, or sometimes also called sectional curvature. Subsection 2.1, the problem in plain terms. This is my best attempt. Consider rulers whose lengths are greater than the... Okay, here we go. I'm going to try this again. Consider rulers whose lengths are greater than the upper bound of any ruler too small to meaningfully measure lengths on the manifold of interest, but also less than being so long that there would be noticeable deformation to the rulers by stretching or bending as the rulers are moved to different positions throughout the manifold. The rulers of these specified lengths are likened to the dxi used to describe the metric being sought. The metric sought is thus a relation of such given rulers that can be used to provide a measurement of notions such as length, area, or curvature that doesn't violate Euclid's fifth postulate nor get confused between situations such as being on a cylinder or a flat plane, depending how the situation is interpreted. Subsection 2.2, now these are definitions pulled straight from Intro to Smooth Manifolds by John Lee. First, here are some definitions from concepts from smooth manifolds and modern, that is, after circa 1950, Riemannian geometry related to what is discussed here. Consider the notion of smooth maps in the context of Euclidean spaces. If capital U and capital V are open subsets of Euclidean spaces, Rn and Rm, respectively, a function capital F from U to V is said to be smooth, or C infinity, or infinitely differentiable, if each of its component functions has continuous partial derivatives of all orders. Topological manifolds are regarded as topological spaces, capital M say, that are Hausdorff spaces, namely, for every pair of distinct points P and Q that are in M, there are disjoint open subsets U and V of M, such that P is in U and Q is in V. These topological spaces also have a countable basis for the underlying topology and are also, thirdly, locally and dimensionally Euclidean. That is to say, at each point of the topological space, there is a neighborhood that is homeomorphic to an open subset of Rn, let's say, or conversely, an open ball in Rn, or possibly even just Rn itself, in that homeomorphism for the third condition for a topological space to be a topological manifold, locally and Euclidean. Next, a coordinate chart or just a chart on M is a pair, U and Phi, where U is an open subset of M and Phi maps U to U hat. And Phi is a homeomorphism from U to an open subset U hat, which is just the image of U under Phi, which is a subset of Rn. An atlas for M is a collection of charts whose domains cover M. If U Phi and V psi are two charts such that the intersection of U and V is non-empty, the composite map of psi and phi inverse, which maps the intersection of u and v under phi to the map of the intersection of u and v under psi is called the transition map from phi to psi. Two charts are said to be smoothly compatible if either the intersection of u and v is empty, or the transition map, psi composed with the inverse of phi, is a diffeomorphism. An atlas capital calligraphic A is called a smooth atlas if any two charts in A are smoothly compatible with each other. A smooth atlas A on M is maximal if it is not properly contained in any larger smooth atlas. If M is a topological manifold, a smooth structure on M is a maximal smooth atlas. Ooh, there we go. We have the first typo. M-A-C-I-M-A-L. Who do I think I am? A smooth manifold is a pair, M and the capital calligraphic A, where M is a topological manifold and A is a smooth structure on M. Riemannian manifolds are smooth manifolds equipped with Riemannian metrics, which are simply smoothly varying choices of inner products on tangent spaces, which allow for the measurement of geometric quantities such as distances and angles. The notion of curvature and its relation to topology is the central unifying theme of current Riemannian geometry research. The mathematically rigorous generalization of the notion of geometric objects that intersect other geometric objects at only one point might begin with tangent lines to plane curves. These curves get represented as functions, and the tangent lines are expressed as derivatives of these functions. At a given point P on a curve, there is a tangent gamma prime along the curve at that point. Many circles can be coincidentally tangent to the tangent gamma along the curve at that point. The circle among these whose own tangent at the point P is the same as that of gamma is called the osculating circle. Curvature is thus kappa equals 1 over capital R, where capital R is the radius of the osculating circle. The next step is to develop this notion of curvatures for curved two-dimensional surfaces in three-dimensional space. This can be done with what are called the principal curvatures. Kreyszig's differential geometry defines principal curvatures starting with normal curvatures, which are the curvatures of the curves intersecting normal sections of the surface of interest at a particular point. The curvature in the directions for which this normal curvature becomes extreme are the principal curvatures. It turns out that principal curvatures are not intrinsic, which is a property paramount to Riemannian geometry. Properties of surfaces in R3 are called intrinsic if they are preserved by isometries, that is to say, maps from one surface to another that preserve lengths of curves, in this case. Roughly speaking, this means intrinsic properties are those that can be gleaned from a microscopic local perspective rather than a macroscopic global perspective. To see this, consider the normal sections and principal curvatures of a plane versus those of a cylinder. Subsection 2.3. Historical context. In spite of principal curvatures not being intrinsic, in 1827 Gauss discovered what is now known as the Theorema Egregium, namely that the so-called Gaussian curvature, which is capital K equals kappa 1 times kappa 2, or the product of the principal curvatures, so those kappa 1 and kappa 2 are the principal curvatures. Gaussian curvature is intrinsic by showing that it depends only on what is called the first fundamental form. Consider a component of the first fundamental form, namely g sub alpha beta equals the vector x sub alpha scalar product with the vector x sub beta, where the x vectors are tangent vectors to a surface and where alpha and beta are indices of principal directions on that surface. More precisely, let t parameterize a function u of x sub I, say, representing position on the surface, and let alpha and beta be members of the set of indices of principal directions in this case, which I denoted here as the set of these indices I for the vector x components of this vector valued function u. So we have all of these vectors x sub I, which are in terms of t, and if we have the set of all of these indices I, then we would find alpha and beta in that set. And u is a function in terms of all of these x sub I. Hopefully that makes sense. For the moment, limit to just 2 dimensions and say that there is only x sub 1 and x sub 2. In this case, the first fundamental form may be presented as ds squared equals capital E times du squared plus 2 times capital F du dv plus capital G times dv squared, where capital E, capital F, and capital G are metric coefficients. Stretching of the surface amounts to conformal dilation of E, F, and or G possibly, and deforming K, deforming Gaussian curvature, amounts to bending the surface. The discriminant of the first fundamental form then would be defined as g sub 1 1 times g sub 2 2 minus the square of g sub 1 2, where g sub 1 1, g sub 2 2, and g sub 1 2 are referred to as components of the first fundamental form. So consider along the lines of the definition of the first fundamental form in terms of the scalar product of x sub alpha and x sub beta, a different dot product of vectors at a point on a surface referred to as the second fundamental form. So in the first fundamental form, it's the dot product of x sub alpha and x sub beta. But in the case of the second fundamental form, we have that b sub alpha beta is equal to, oh, here's another typo. That should be alpha and beta instead of a and b. But we have x sub alpha beta scalar product with n, where we'll see what n is down in the caption to these expressions here. But for the moment, the second fundamental form is also equal to negative x sub alpha scalar product with n sub beta. That is to say, this x sub alpha beta is the second order partial derivative, once with respect to alpha, once with respect to beta. But we also have on the far right of line 6, negative x sub alpha scalar product with n sub beta. Anyways, going on here, we have the next line below, we have b sub alpha beta. Another way of writing the second fundamental form is equal to a fraction where in the numerator we have a determinant where the first column is x sub 1, the second column is x sub 2, and the third column is x sub alpha beta. And then the denominator of this fraction that has the determinant in the numerator, the denominator is the positive square root of the discriminant of the first fundamental form. So line 5, basically take the square root of that, keep it positive. That is the denominator for that form of the second fundamental form there in line 7. So this is the elaboration we've been waiting for. X sub alpha beta is equal to partial square u, partial u alpha, partial u beta, and n is the unit normal vector on the surface, n, which is equal to a numerator of x1 cross product with x sub 2 all over the magnitude of the cross product of x sub 1 with x sub 2. And again, similar to how we have a discriminant for the first fundamental form, there's also the corresponding discriminant of the second fundamental form, which likewise b is equal to b sub 1 1 times b sub 2 2 minus the square of b sub 1 2. We have another way of writing what we've already seen twice now. The first time we saw on page 1 here, Gaussian curvature equal to capital R sub 1 2 1 2. We'll figure out what that means in just a moment, all over G. Second time we saw Gaussian curvature, right at the beginning, capital K equals kappa 1 times kappa 2. Now this is the third time. So by means of, why did I unroll the definitions for the first and second fundamental forms here? Well, here you have it. We can rewrite Gaussian curvature capital K as equal to the discriminant of the second fundamental form over the discriminant of the first fundamental form, B over G. However, line 7, why did I, do this one? Well, the reason why is because it shows that the discriminant of the second fundamental form depends on the first fundamental form only. Therefore, Gaussian curvature, capital K, as it would be referred to throughout this document, depends on the first fundamental form only. The explicit representation of Gaussian curvature K only in terms of G sub alpha beta is sometimes called the equation of Gauss. And this is partly included for nostalgia's sake because I remember back in section 40-something when I read this equation of Gauss for the first time, that was one of the most challenging things to read out loud from the entirety of the Differential Geometry by Erwin Kreyszig book, which I've been reading out loud in its entirety. I'm getting close, to finishing it here. But The equation of Gauss right here, look at that. That was difficult to read out loud. I'm going to do it one more time for you guys right here, right now. Capital K, Gaussian curvature, is equal to 1 over g squared times a determinant, which is 3 by 3. And I'm now going to read column-wise. Starting with the first column, we have g sub 1, 1, and then we have g sub 1, 2. And then we have 1/2 times partial g sub 1, 1, partial u1. That completes the first column of the first determinant here. The second column of the first determinant is g sub 1, 2, and then g sub 2, 2, and then the third entry of the second column is a quantity of partial g sub 1, 2, partial u1 minus 1/2 partial g sub 1, 1, partial u2 closed quantity, which then completes the second column of the first determinant. The third and final column of the first but not final determinant goes like this. Partial g sub 1, 2, partial u2 minus 1/2 partial g sub 2, 2, partial u1. And then the second entry of the third column is 1/2 times partial g sub 2, 2, partial u2. And then the third entry of the third column, which is the final entry of this 3 by 3 determinant, is the quantity negative 1/2 times partial squared g sub 1, 1, partial u2 squared plus partial squared g sub 1, 2, partial u1, partial u2 minus 1/2 partial squared g sub 2, 2, partial u1 squared closed quantity, which then completes the first determinant. But then the equation of Gauss continues with a second determinant term, which is minus 1 over g squared times another 3 by 3 determinant, which I will again read entry-wise, column by column, starting with the first column, g sub 1, 1, then g sub 1, 2, then 1/2 times partial g sub 1, 1, partial u2. And then in the second column, g sub 1, 2, and then g sub 2, 2, and then 1/2 times partial g sub 2, 2, partial u1. And then in the third column, 1/2 partial g sub 1, 1, partial u2, and then 1/2 partial g sub 2, 2. Ooh, we have the third typo. That second index on the component of the first fundamental form got lost from being a subscript, and now it's just floating there on the numerator. Anywho, 1/2 partial g sub 2, 2, partial u1, and then 0. And that's the equation of Gauss. This is effectively what Gauss's Theorema Egregium states. Theorem 1. Theorema Egregium by Gauss. The Gaussian curvature, capital K, of a surface is independent of the second fundamental form, but depends only on the coefficients g sub alpha beta of the first fundamental form and their first and second derivatives. And egregium looks similar to the word egregious, but it actually means remarkable, because when Gauss found out the Theorema Egregium, he found it remarkable. Riemann's Über die Hypothesen effectively extends Gauss's differential geometry of surfaces to n-manifolds while simultaneously advancing a classification result of these n-manifolds in the case of constant Gaussian curvature. Riemann accomplished this in Über die Hypothesen by laying the conceptual groundwork of Riemannian metrics on Riemannian manifolds and the associated Riemann curvature tensor. This is not the kind of terminology that Riemann himself used in 1854 to advance these ideas for the first time, however. Riemann's habilitation thesis often refers to measure relations and magnitude relations. So-called magnitude relations in discrete spaces are obtained by counting. Magnitude relations in continuous spaces, on the other hand, are obtained by measuring and comparing. On the one hand, the Pythagorean theorem provides a way of measuring lengths, that is, magnitudes, on flat planes. On the other hand, Euclid's fifth postulate on the eventual intersection of parallel lines was troublesome for the global geometry of surfaces in the mid-1800s. Riemann surmounted this by conceptually advancing upon his advisor Gauss's Theorema Egregium. In fact, the second fundamental form that was shown to be not so fundamental after all to Gaussian curvature K can now be represented as merely a component of the Riemannian curvature tensor divided by the discriminant of the first fundamental form, which is what we saw at the beginning. Capital K equals capital R sub 1, 2, 1, 2 all over lowercase g. An approach to determining an intrinsic metric or measure relation on n manifolds of constant Gaussian curvature might perhaps be to scale the simplest feasible locally Euclidean metric in a way that preserves angles. In other words, an approach to an intrinsic metric on a surface that can give insight into its curvature might be to conformally scale the infinitesimal n-dimensional Euclidean metric to obtain an infinitesimal n-1 dimensional metric on a surface in that space. In Part 2, Section 4 of Über die Hypothesen, under the header Flat manifoldness may be treated as a special case of manifoldness with constant curvature, Riemann announces that he has more or less just succeeded with that approach. The result he presents at the end of Section 4 in Part 2, as we saw earlier, is ds equals a numerator of the square root of the sum of all of the dxi squared all over a denominator of 1 plus alpha over 4 times the sum of all the xi squared, where alpha is equal to 4 times Gaussian curvature capital K. Subsection 2.4, mathematically framing the problem. The Riemannian metric is the sort of relation being sought which together with a smooth manifold makes a Riemannian manifold. This Riemannian metric can pose a Riemannian curvature tensor, which then can be used to compute curvature. The tensor calculations of Riemannian geometry were not laid out by Riemann himself, but rather afterwards by Gregorio Ricci-Curbastro and Tullio Levi-Civita. Ricci-Curbastro introduced the modern notion of the Riemannian curvature tensor. Levi-Civita would introduce, among other things in this subject of mathematics, what is now known as Ricci curvature. Ricci curvature, capital R sub ij, is a tensor that is a trace resulting from a tensor contraction of the Riemannian curvature tensor, capital R sub ikj, and then a superscript, or that's actually really a contravariant index, since these are all tensors. So for the Riemannian curvature tensor, capital R, we have the covariant indices of I, k, and j, and then we also have a contravariant index of k. Levi-Civita introduced the Ricci curvature to simplify the calculation of the full rank 4 Riemannian curvature tensor. Thus, the surfaces of non-zero constant curvature can be explored through the Riemannian curvature tensor of Riemannian manifolds with Riemannian metrics that are the Euclidean metrics scaled by a constant conformal factor. First, the Riemannian curvature tensor is contracted to a statement of Ricci curvature. Then, the statement of conformal transformation of the Euclidean metric leads to the Ricci curvature involving a PDE of the Laplacian in the form of Louisville's equation. I always end up mistakenly saying Louisville, but it's Louisville's equation. To illustrate this, consider, for example, a specific instance of the metric on an n-1 dimensional surface embedded in n-dimensional space, namely a 2D surface embedded in a 3D Euclidean space. The case of computing curvature in n-dimensional space for n equals 3 would require defining n-1 equals 2 principal coordinate directions on the 2D surface of interest. In other words, a manifold embedded in n-dimensional ambient space takes at most n-1 coordinates to unambiguously define position upon the manifold. The example 2D surface might thus be said to be parametrized by coordinates lowercase u and lowercase v. The metric would be given by ds squared equals g sub ij, then times dxi, then times dxj. This would just be ds squared equals du squared plus dv squared in the case of a flat plane. For surfaces of non-zero curvature, scaling the flat metric by a general conformal factor, namely ds squared equals e to the 2u, then times the sum of all dxi squared, which could be written as being equal to lambda times the sum of all dxi squared, will be considered. Louisville's equation appears in the study of isothermal coordinates so far as the independent variables are the coordinates being mapped, for which refer to section 62, titled Conformal Mapping of Surfaces into a Plane from Kreyszig's Differential Geometry. While the exact solution function f can be described as the conformal factor with respect to the flat Euclidean metric, its general form is delta sub 0, or I don't know, I'll just call it like Laplacian naught, perhaps. Laplacian naught of the log of f is equal to negative k times f squared, where capital delta naught or Laplacian naught here just denotes partial squared partial x squared plus partial squared partial y squared. Note that the more general Liouville equation may be written in terms of the so-called Laplace-Beltrami operator, which we could call Laplacian sub LB, which is equal to 1 over f squared times Laplacian naught, so that we obtain Laplacian sub LB of log of f is equal to negative k. The Laplace-Beltrami operator is the topic of Kreyszig's section 75 titled Differential Parameters of Beltrami, which is the next section that I'm going to be reading out loud once I get back to this bad boy here. The Laplace-Beltrami operator was not included in the scope of Lee's Intro to Riemannian Manifolds book, but it is indeed covered as a subtopic within the context of Hodge theory in Peter Peterson's Riemannian Geometry book. Note the following result from Chapter 7 called Curvature under the heading Curvatures of Conformally Related Metrics in Lee's Intro to Riemannian Manifolds book, which we find on page 217. And specifically in this definition, line 16 here will come up again when we get to line 94 in the actual calculations of filling in the gaps here. So all I'm going to actually read is line 16 here. So we have capital S tilde is equal to e to the negative 2f, then times the quantity capital S minus 2 times the quantity n minus 1 closed quantity Laplacian of f minus the quantity n minus 1 closed quantity n minus 2 closed quantity, then times the magnitude of df squared sub g close outer quantity. It's almost like I've been practicing reading all this math out loud for the last year, like every single weekend. Section 3, the problem. Consider constant Gaussian curvature so that the locally Euclidean metric of the manifold is scaled by a conformal factor. Scalar curvature results in a PDE in the form of Liouville's equation, whose solution is the metric being sought for the manifold of interest. Assume from the form of Liouville's equation for isothermal coordinates and perform a change of variables, namely by log f to u, to the earlier form of Liouville's equation, the more general form, to obtain Laplacian naught equals negative capital K times e to the 2u. The conformal scaling by curvature that is of interest is described by ds squared equals e to the 2u, where u is in terms of x1 through xn. Then we have times the exponential, the sum of all the dxi squared, with, like I said, u being a function in terms of x1 through xn, which we will sometimes write as being u of r, where r is just the square root of the sum of all of these xi squared. There is a fourth typo. We have some atrocious one-sided parentheses going on here. Continuing on. The form of our function u in terms of x1 through xn is the proper exact solution to the PDE above. But in earnest, the exponential portion, e to the 2u, will effectively end up being computed. Constant Gaussian curvature, capital K, with scalar Ricci curvature, capital R, equals n times the quantity n minus 1 closed quantity, then times capital K, is sought. The choice of metric scales the flat locally Euclidean metric by e to the 2u. The problem could be written less precisely instead as Laplacian naught equals negative k times lambda of u in order to make calculations simpler. However, specifying in what I just said that lambda of u is equal to e to the 2u will make the calculations more specific, and this will lend to directly connecting to Riemann's 1854 result. After all, the complex exponential function is analytic for every complex number that may be input. Namely, the power series expansion of the exponential function converges for any complex number, which here is simply just chosen to be 2u. Subsection 3.1, Formulae from Kreyszig's Differential Geometry. Now, these are all equations that I copied directly from the book here, okay? So keep in mind that, this book came after Riemann. This is basically written 100 years after, because the first edition of Differential Geometry by Erwin Kreyszig came out in 1959. Bernard Riemann, that's 1854 for Über die Hypothesen. There is not a direct working out of the results in Kreyszig's differential geometry, right? He kind of alludes to it, I guess, at the end, like the very end of the book, with stuff about constant Gaussian curvature, but it's not what I'm about to show you guys here. But we're connecting the dots. We're filling in the gaps, right? So I grabbed equations from the book. Right here, this is just notation for partial derivatives, notation for Laplacian with Kronecker deltas going on. Same for gradient. Magnitude squared of the gradient will appear as doing the sum on the index m of products of these kinds of partial derivatives here. Because here I'm not saying this is u to the m as in m and exponent, but it's kind of like I said earlier, they're contravariant indices. There's also like implied here the whole Einstein summation notation convention here, but I'm pretty sure that I skirted around that, or I didn't like do stuff here where that's a problem. Like, I'm pretty sure I did everything correctly. Sometimes it will be written r squared equals the sum of x squared, all the different x squared. There should be like another index on this x that's implied here, for instance. It should be the letter I, where it's all of your different coordinates, all your different coordinate directions, all your different coordinate tangents you've chosen upon for your manifold. The Kronecker delta, straightforward, everything you would expect there. We kind of went over these. This is like Kreyszig's vector notation for writing these partial derivatives on the manifold, on the surface, if you will. We have sort of like relating those then to Kronecker deltas, because this will come up in calculations. Same thing with if we had first fundamental forms, or these are also called just metrics, really. I think from here on out, I'll just be referring to them as not these G's. It's just not first fundamental forms, as I'll refer to them, but just metrics, basically. And if it's the answer or the Riemannian metric, I'll kind of spell that part out. But anyways, Christoffel symbols of the first kind. This is a capital gamma, but I always read them as Christoffel because there could be like a gamma function or, lots of reasons to use a capital gamma in math. So I'm just going to call it a Christoffel. Christoffel sub alpha beta sigma is equivalent to the scalar product of vector x sub alpha beta with x sub sigma, which is equal to 1/2 times the quantity partial g sub beta sigma partial u alpha plus partial g sub sigma alpha partial u beta minus partial g sub alpha beta partial u sigma closed quantity. And I'll just say it right now, Christoffel symbols are not tensors. That makes this, it just adds a layer of possible confusion, or it, at the very least, like for me, it just meant it took me a little bit longer time in order for that stuff to polymerize in my mind, if you will. But Christoffel symbols are not tensors, but we're going to use Christoffel symbols to express a tensor, in fact, namely the mixed Riemann curvature tensor, as we'll see below here. But I'm getting ahead of myself. We have transformation laws for these Christoffel symbols. Again, layers of confusion because there's transformation laws for tensors. And they're called the same thing, raising indices and lowering indices. But it's just if we multiply metrics through on these Christoffel symbols, then we can rewrite these indices as being so-called contravariant or covariant indices. Because I guess under the hood, there are contravariant or covariant indices on like the partial derivatives that the Christoffel symbols are expressing, but it's just that Christoffel symbols themselves are a particular combination of particular partial derivatives. Anyways, some might say this is the belle of the ball here. This is the mixed Riemann curvature tensor. We're going to get our hands dirty with this one here. This is capital R with covariant indices alpha, lambda, beta, contravariant index sigma. This is equal to, in terms of Christoffel symbols, partial Christoffel sub alpha beta superscript sigma partial u lambda minus partial Christoffel sub alpha lambda superscript sigma partial u beta, and then plus Christoffel sub alpha beta superscript kappa times Christoffel sub kappa lambda superscript sigma minus Christoffel sub alpha lambda superscript kappa times Christoffel sub kappa beta superscript sigma. We are now going to solve the problem, and if you think the Greek character indices are a little bit atrocious, don't worry. In a few lines, they're going to go away, and we're going to be working with I's, J's, K's, L's, and M's, but still with Christoffel symbols and tensors, so solving the problem. This is hopefully an insightful light bulb moment for some of us. Scalar curvature results in a PDE whose solution is the metric being sought for the manifold of interest. Scalar curvature of a manifold comes from the Ricci tensor, which comes from the Riemann curvature tensor, which starts with Christoffel symbols. And I will say, every single part of the solution that follows you can trace directly from now just these equations from, I'll call this like the equation section up here, which inevitably came from the book, even specifically like the formula sheet in the back of the Kreyszig book. So we're going to start with the definition of Christoffel symbols of the first kind, and we're going to do the raising of an index on it here, and we compute that guy out, and then we insert in this generic metric component where we start playing with the e to the 2u that we have. We put this generic metric component in, we change the letters around as needed in order to get these three partial derivatives that are going on the inside of this quantity here for this Christoffel symbol. And what do you know? After we do all that, we get this Christoffel sub ik superscript L equals Christoffel superscript Lm times the quantity. We can simplify these Kronecker deltas, and we keep simplifying, and we then get to the point where we're like, okay, we're going to compute every single term of the Riemann curvature tensor, and we're just going to crank away. And it's like I said, I get down to this part here and I'm like, oh man, I'm really deep, and I was sort of like, I'm gonna just see what AI says, if it could be any help. It was a little bit, it's kind of like maybe when I was coming up through school, I would have wished that there was like a calculator that you could just literally type in as if what we now think of as like Mathematica, and it would like simplify, do the algebraic symbolic manipulations for you. But then like the most help I got from AI on this was just like double checking that I didn't, screw up doing this basically like elementary school algebra of like, can I multiply out these, there's three different terms added together. Each term has two terms multiplied together, and then we have two sets of parentheses. It's like, can you PEMDAS your way out of that and keep, all of it straight? It's like, yeah, it's kind of tedious from one way of looking at it, but it's like, if you failed doing that kind of stuff in elementary school, it's like, yeah, good luck filling in the gaps for Riemann's habilitation thesis, which is like a huge revolutionary piece of mathematics, you dumb piece of shit. Anyways, so you go through and, we're calculating the square of the magnitude of this del u. We've got this nabla operator. I just like saying it, nabla. It's a fun word to say. It's just, once you realize everything that you need from the equation sheet, and then you just literally spend several weekends of your free time doing it all out, pen and paper, and then you turn on OBS and you make a fool of yourself on a 6-hour-long YouTube video. And then I don't know, This right here is like very solid, I feel like, because then we come down here, we finally like computed out this, where is it? Yeah, right here. Okay, this is what I was even talking about towards the beginning. All right, we've expanded out the Ricci curvature tensor. Now we're going to do a contraction on it. So that means you're going to sum through on a dummy index K, let's say, basically. And so it's just more excruciating algebra, frankly. It's kind of like what makes this different from like algebra, let's say in elementary school or something like that, really is like understanding symbolically how to handle like these mixing covariant and contravariant indices, but then they somehow algebraically combine into Kronecker delta symbols, which like Kronecker delta, that's not necessarily like a revolutionary idea, but then being able to connect the dots and get some of these aspects of the calculation correct requires maybe like a deeper understanding on like the conceptual side of like what is this math all about, because like any middle schooler, you could crank out whatever calculations you give them if you just tell them the rules for it. But it's like it honestly took me a few months maybe to really appreciate how Christoffel symbols are not tensors. Okay, so, and getting all of this stuff like rank 4 Riemann curvature tensor was like rank 2 Ricci curvature. I mean, for me, it wasn't easy. For some of you, it might have been easy. But anyway, we get down here and we finished the tensor contraction. So now we have ostensibly Ricci curvature. But then this is what I was saying earlier in sort of like the introduction sections, if you will, is that if we look at this definition, which even came from a math book in a section that was like the conformal transformation of curvature or whatever, here we go. We have this e to the minus 2f. Boom, just move it to the other side. And then what do we have right here? Oh, flip flop across this minus sign here. So we have n minus 1, n minus 2. Oh, what do we have? N minus 1, n minus 2. Oh, what do we have here? Square of nabla u. What do we have here? Oh, it's just just so happens that John Lee calls it a DF. And it's like we can probably infer that these are basically the same thing. And then right here, oh, Laplacian of u, Laplacian f. Big whoop, big whoop. We can see, oh, we got an F here, F here, F here, U there, U there, U there. Got him. Got him. Anyways, so we're like, okay, what are we going to do with this now? We're going to crank our way to the end with algebra. Divide through by -2 times the quantity n minus 1. We're getting so close to the Louisville equation. Hopefully you could just taste it. It's right there. And so now we start considering things that are going on with like the specifics of the problem. So I might as well just read that. The radial symmetry of capital Sn, that's just referring to the n-dimensional sphere, n-dimensional unit sphere. It could be any sphere, but then you could change it to a unit sphere if you want, and then you're like, that didn't really change much. Simplifies the square of the magnitude of del u to be just the square of u prime. And the Laplacian of u is just u double prime plus n minus 1 over r times u prime. Thus, this PDE in the form of Louisville's equation may now be written as this guy right here. And we'll say, you know what? At this point, this guy is good enough that we're going to plug in the general stereographic projection form solution. In this entire appendix, I basically derive the stereographic projection formulas from scratch. It's pretty nice. It's pretty easy as long as you just remember what to do here. This is the mid-sagittal section of the stereographic projection of Z. I keep on saying this over and over. It's like if the unit sphere were your head and then you're imagining that like halfway through your face is like your nose, let's say. Complex plane is just like, you're in a pool of water. It's the surface of the water. It's up to your nose, okay? That's how I'll explain that. But in the mid-sagittal section is if we take a buzz saw straight down the vertical middle of your face, and then we split your head like a piece of fruit open. Boom. And now we're looking at the side. Do we buzz saw, split open? That's what we're looking at here in figure 1. And the key here is to look at the triangle origin O, North Pole N, Z, and then realize that that is similar to the triangle Z, Z prime, Z underscore here. And then looking at the ratio of this leg to the ratio of this leg, because we know that this one right here, unit sphere, length is 1. Yeah, because then you just come up with these ratios that you can use to compute away, do more computations. But then it's like, look at this. The capital X, capital Y here, those are the equations for the X and Y of this projected guy down here on the complex plane. Because you could say that this Z underscore, that's like the projection of the point Z that is being projected. And then this Z prime, since we're looking at this, this is like if you had arrows that you're shooting into the screen all along what's the x-axis here, those arrows, you could bundle them together and you would have the complex plane. Very intentionally stated. Pencils, bundles, anyway, but look at that. It's like, all right, you just write, instead of x squared plus y squared, just generalize that Pythagorean theorem and just have it the sum of x squareds of all the different components. And then it's like, oh, you've got a scalar on the top of 2. You could factor that out. I say that so nonchalantly because guess what we're going to do in just a sec? We're going to factor out some stuff like it's magic. Anyways, so here we are. We're like, okay, we're inspired because we've got this really trimmed down, conditions enforced PDE here. And we're going to crank things up to 0. We're going to crank things down, actually, because we're sliding down. We've already done the hardest parts of the computation at this point. We're just sliding down. It's like that last green run when you're skiing. If any of you have been skiing, and it's like pretty much all of the ski runs, what do you call it? Like they funnel into like one run that's like down the face of the mountain, that where you're some normie loser who doesn't want to do anything except for just sit and wait while everyone else is skiing, and you see everyone coming down the face of the mountain. That run where it's like, it's maybe if you've never been skiing before, it looks like, oh, that's intense, but it's really like the easiest finale, basically. That's basically what this is. It's like you're coming down the face of the mountain, and it's like, you're like, woo, great. We were at the top, and it was like, holy cow, Riemann curvature tensor, Ricci curvature, and just wrapping our head around Christoffel symbols and all that stuff. Wow, that was a lot. But now this is it. We're just skeeting into the end zone because you just plug in the solution, and then we're like, oh my gosh, when we do that, we can start picking out what some of these indices in this general stereographic projection form solution are. And this is what I'm talking about. We're like, oh, a squared equals 4 is like the last thing we computed. And then we're like, okay, we've got B we can still kind of set, and then we've got alpha we can still kind of set. Let's choose it to be 4K, and we're going to choose B to equal 4, because look at what happens when you do. You just skeet your way, and you can just factor that 4 out, and you just, oh, nice. You just get just right there. There it is, Riemann's result, and we got it. Thus, the conformal factor adjustment to the flat metric by the constant curvature. Boom, there it is. Section 5. That's what it is. The end. You see that right there? K equals R over G implies all this right here. looks like stereographic projection, because it's like we can kind of see now looking back how we got here. It's like, okay, on the left hand side, just multiply G over to the left, and then we're looking at this and we're saying, okay, now we're going to just compute this out, and then, oh no, we don't know what G is. We know what K is because it's constant curvature, and then we're going to, piece things together. And I'm probably going to cut out a lot of this nonsense, but I don't know. I need to fix my website, and then I'll upload this. But I don't know. Hope you guys found this entertaining at least. But I felt like this was like, it was I don't know. It was really profound to go through all the details of this, to be honest. But it gives me confidence that I can keep studying, self-studying differential geometry and Riemannian geometry, and that I'm not just like completely deluding myself, and that I'm not just like making it up. And I'm going to be that guy who walks around at the grocery store with differential geometry, but it's just a total cope because you don't actually understand anything that's in the book. Like, nah, I ain't about that. I'm about that real, authentic, sincere, I understand what's going on here. I'm not like, freaking Terrence Tao or anything like that, but, I ain't no schmuck either. So on that note, see you guys in the next one.